All right, let's look at the second topic, which is two-variable data. So the big picture there is you're given a data set centered around two variables, and you want to describe the relationship between them. So there are three main ways to examine a relationship between categorical data. Categorical data is the data that is put into categories. So there's frequency tables, segmented bar graphs, or Mosaic plots. So the relationship between gender and political affiliation for the 100 senators in 2020, I can make a frequency table. So one of the categories is gender. So I've got male and female. And the other one is political affiliation, Democratic, Republican, and Independent. And I can see that there are 29 Democratic males, 16 Democratic females, 44 Republican males, 9 Republican females, and 2 independent males, and no independent females. Now, I can make a bar graph, segmented bar graph that shows this relationship. Now, from this, I've got gender at the bottom, and then I've got political affiliation over here, and you really can't tell if there's more male or female senators, but you can tell that there are more female Democrats than Republican Democrats. So you can tell, you can talk about things within a category, but you can't compare the straight numbers between the two. Now here is a Mosaic plot that lets you account for this idea. So now you can look at the shear area, and you can see the biggest area by far is this one right here, which is Republican males. So there are more Republican males than any other category, subcategory in the Senate in 2020, followed by Democratic males. And you can see independent males is the smallest, followed by Republican women. So Republican females. Now, most of this unit is going to focus on relationship between quantitative data. So for example, the relationship between square footage and price of a house in a neighborhood in Blacksburg, Virginia. So like that's just what this example is. And we have a scatter plot that shows the relationship between those two. When describing such a relationship, I want to focus on LSD, which is linearity, strength, and direction. So linearity says, is the best model for the data going to be one that's a line? Strength is, on average, how close are my points, my actual points, to my predicted points. So for example, like here, the predicted value is very close to the actual value, pretty much identical. Over here, it's like quite far away. So on average, the closer they are, the closer the actual values to the predicted values, the stronger the relationship. Direction means that as one variable increases in value, we expect the other variable to increase in value as well. So this would be a positive direction. This is what a negative direction would look like. So going down. So additionally, you want to discuss anything unusual going on, like clusters or outliers. So the correlation between two quantitative variables describes the strength and direction of the association. So for the relationship above, my R is 0.856. Now R is always going to be a number between and including -1 and 1. So -1 is a perfect negative correlation. 1 is a perfect positive correlation. So And it's important to note, just because a correlation coefficient is -1 or 1 or close to that doesn't mean that a linear model is appropriate. It's always important to look at the actual scatter plot of the data. So this would be a strong positive correlation, positive relationship. Now, the line of best fit for our relationship between square footage and price is this right here. So the slope of that is 0.07096 and the y-intercept is 154.1247. Now you need to know how to interpret that in context. So for slope, we would say for each additional square foot of house in the neighborhood, and this is important, we would expect the price of the house to increase by $70.96. So 0.07096, but this is in thousands. So when I multiply the two, I get $70.96. Now in the context of that problem, it makes sense. So you're basically paying like $71 for each additional square foot. So that makes sense. The y-intercept, a house with 0 square feet would cost $154,000 in that neighborhood. That doesn't really make sense, except if we're talking about maybe like the cost of the land. So the land itself could be $154,000, but it doesn't really say like how big the acres are, whatever. Most importantly, there we're engaging in some serious extrapolation because the smallest value we have is 1800, so 0 would be way out there. And extrapolation pretty much always is going to be problematic. And the further away you go from the range of the data set, the more problematic it is. So when you extrapolate, you make a prediction using a model that is outside of the range of the model. Extrapolations are often problematic, especially the further you go. Thus, trying to predict the value of a house in a neighborhood that has 1,200 square feet would be relatively inaccurate. So my range here goes from 1,800 to 3,800. So if I wanted to predict the value of a house that has 1,200 square feet or 12,000 square feet, that'd be very problematic. It's way out there. Residuals are vertical distances between individual points and a model. So the formula for a residual is actual minus predicted, and the plot. So let's look at the, here's the plot we have before. Let's highlight 2 points, point A and point B. Point A has a negative residual because it's below the line. Point B has a positive residual because it's above the line. By the way, if this was point C would have a residual that is very close to 0. Also, the value of A is larger than B since it's further away from the line. It's like the absolute value of that. Here is a residual plot. As you can see, this is point C. It's right on the line. Point B is right here, and point A is right here. There's no obvious pattern to this residual plot. There's no obvious pattern to the residual plot, which supports a linear model. So if there's no obvious pattern to a residual plot, that is like evidence for the fact that a linear model is good. Finally, the coefficient of determination, or R squared, gives insight into the proportion of variation that in Y that can be explained by the variation in X. So for example, if I take my correlation coefficient 0.856, square that, I get 73.3%. So I would say 73.3% of the percent of the variation in the price of a house can be explained by variation in square footage. And the remaining 26.7% is due to some other variables, like the build of the house, interior modeling, how nice the bathrooms are, if there's a jacuzzi, etc., etc., etc. So That's some general insight into working with two variable data.